Yeah. Okay, so just as our warm up today, looking at last year's materials on right angle triangle trigonometry, I'd like you to solve this right triangle. You should use your calculator for this one. I'm just going to pause the video for a minute while you work with that. There we go. Good luck. Here we go. All right. So we're looking just to do a bit of revision of our trigonometry. Our trigonometry is based on our three functions: the sinus function, the cosinus function, and the tangent function. So these are defined due to their. You should have looked a little bit at similar figures and similar triangles. And when you have a similar triangle, first, when you have set angles, then there's going to be a set ratio between the sides. And this set ratio between the sides can be used to define the trigonometric functions. And this is how we define them. So we say that the sine of theta is equal to the opposite over the hypotenuse. The cosine of theta is equal to the adjacent over the hypotenuse. And it's these ratios between the sides which is what creates the definition of each of these functions. And the tangent is opposite over adjacent. So the first thing you need to do with a question like this one is decide what to name the sides. So in a right angle triangle, you've always got a right angle, so the longest side is always opposite that. In any triangle, the longest side is always opposite the largest angle, and vice versa. So in this one, this is the largest angle, so this one is the hypotenuse. Next, it doesn't matter which angle you name. You can name any angle, but typically we will have one angle in the question, which is specified like this. So we will define everything in relation to this angle at this particular point. This is going to be our theta. And we're going to need to name the sides. The side that lies opposite theta is called the opposite, and the side that lies adjacent to the theta is called the adjacent. Adjacent means to the side. If you're standing adjacent to a building, you're at the side of it. So then we need to, at this point, we're going to need to use our calculator a little bit in order to find the values. My calculator is here. With your calculator, one of the most important things is to see what symbol is up here. At the moment, we're working in degrees. We haven't been introduced to the concept of radians. The standard unit of measurement for an angle is radians, not degrees. Degrees was developed by the Babylonians. The Babylonians lived in sort of Iraq, around about in the period when 0 to 1000 BC. I can't quite remember, somewhere like that. They had a base 60 counting system. So in their counting system, they didn't have a place value system like we have. We have a base 10 place value system. We count from 0 to 9, and at that point we put a 1 in the next column, and then we keep going. They counted in base 60, so they would create different symbols, which would then create all the numbers from 0 to 60. After that, they would move to the next set of symbols, which would count from 0 to 60. They knew a lot of math really early on, and they knew that there was 365. They didn't even know there was 365 days in it. They knew there was a little bit more. Their astronomy was absolutely excellent. They knew that you needed a leap year and everything. So some people misassume that there's 360 degrees in the circle because they thought it was 360 degrees in 360 days in the year. They didn't. They knew much better than that. Their math was fabulous. However, 360 is a very divisible number. It's divisible by 2, it's divisible by 3, it's divisible by 4, it's divisible by 5, it's divisible by 6, it's divisible by 8, it's divisible by 9, it's divisible by 10, it's divisible by 12, it's divisible, it goes on and on. It's a really divisible number. So they're like, this is a sensible number to use. It's not like the imperial system where they decide to have 3 feet in a yard, 12 inches in a feet, and let's just make it different. How many quarts in a gallon and so on. And if you really dig into the imperial system, there's 2 different gallons. There's 2 different pints. The US pint and the British pint are not the same size. The US gallon. So it's great. 360 is a great number. But anyway, we'll see radians later and we'll see why. So just using these values, we can plug these in, use these simple formulas, and get our answers. So firstly, we're asked to find ij. Ij is the hypotenuse, and we have the opposite. So if we have the opposite in the hypotenuse, we're going to be using this formula here. So we can say that the sine, what are we after? We can say that the sine of 49 degrees is equal to the opposite over the unknown that we're after. And then we could rearrange this and solve. So that's going to tell us that 7 divided by the sine of 49 is the answer that we're looking for. If you get an answer that looks like this one, press Control Enter, you'll get a decimal answer. So this is 9.28. So this is, sorry, it was to the nearest tenth. So this is going to be 9.3. 9.3. I'll skip the next one because it's just a repeat using these formulae. The last one, we can do this using the arcus sinus function. But probably what's best off on this one, this is a triangle. The sum of angles on a triangle is 180 degrees. This is 90. So these two angles are always complementary, meaning their sum is equal to 90. So this is 90 minus 49. That's pretty easy. It's going to be 41. Always use the simplest solution. Right. That is your revision for maths here. If you need more help with that, I can recommend some IXL or something. So come and speak to me if you need more help with that one. But we're moving on from that. So what we're looking at now is trigonometry without a calculator. So firstly, let's have a look at this question. Have a go at finding what is the sine of angle I. These two triangles are similar. They're similar. You can see that because two of the angles are the same. So you have angle-angle similarity. So you should come to a solution like this. The sine of I is going to be 33 over 65. We can use, that's a sine value. We can use that value in subsequent calculations without actually finding the angle itself. We can't find the angle like this without either a table of sine values or a calculator. So having a look at some special trigonometric values, this is a, what type of triangle is this one? This is an equilateral triangle. What's the size of this angle here? 60. 60. And this angle here? 60. And this angle here? 60. I'm going to draw an altitude in this triangle, like this, which bisects the base. obviously. So the angle here is 90. Am I sleepy today? Okay, so how big is this angle here?
44, no, 30.
30.
Let's see.
If this length here is 2x, the length of the sides is 2x, and what is the length of
X.
x? So, what is the length of the altitude?
Work squared minus X.
Hold on, take a minute, work it out on a piece of paper, don't shout it out. So the length of the altitude or the height here is going to be x root 3, and it's any multiple of that. So we can define this triangle. This is a special triangle. From this, we get the special right triangle, which have certain ratios between the sides. So we create the ratios here. We don't need to know what the x value is. So if this angle here is 60, this one is 90, and this one is 30, then this base here is going to be 1. This is going to be 2, and this is going to be root 3. And this is one of our special right triangles, because it allows us to define the sine, cosine, and tangent of 30 and 60 degrees. We can even define the 90 as well using it. So what is the sine of 30 degrees? What is the sine of 60 degrees? What is the, while we're here, what is the sine of 90 degrees? What is the cosine of 30 degrees? What is the sine of 60 degrees? Oh, sorry, cosine of 60 degrees. What is the cosine of 90?
Would it be 1? No. The adjacent is way. How do we know if the adjacent is 1 or root?
Yeah, we don't use this triangle for this one, sorry. So imagine if you have a right angle triangle where both these two angles are 90, almost. How long will the adjacent be? So if this one is 90 and the other one is 89.999, you can see that the base is approaching 0. This is where we get that this one is 1, this one is 0, and so on. Okay, so we have a bunch of values. What do we also notice between this pattern?
That they're like connected in some way. Sine of 30 equals cos 60, yeah.
Yeah. What's the relationship between 30 and 60?
is a half a 60.
Oh, they're supplementary.
Almost.
Or
complementary. They're complementary. They're complementary. We will see it later and we'll prove it later. There is a trigonometrical identity or a relationship where we say that the sine of x is equal to the cosine of 90 minus x. This is true for all. This is an identity, so it's true for all values.
negative x.
No, it's this one. There's other ones. We'll see those when we see the unit circle. There's a bunch coming later. The important part is the blue bit here, these values. What's 2x squared if we expand it? So what's 4x minus x squared? Sorry? Because they're ratios. So if they're the angle, we've got angle-angle similarity again. So I'm just simply saying this is the ratio between these ones. So the x, it allows us to enlarge and shrink these ones. So whatever x value is, it's the same x in all of them. So I'm just looking at the only thing that is different other than multiple. So all right-angled triangles with a 60 in them will have some multiple of these three values because they're all similar. Yeah. So x is the multiple, but we don't need the multiple because when I put it into here, so if I put it into here, I put x over 2x, and the x's would cancel. So I just did it to make it look easier.
So how did you simplify 2x times root 3?
Where am I?
Like when you had h squared is equal to 3x squared. There, so how did you simplify it to x root 3?
How do you get rid of x squared?
You square root it. But then relatively...
Because the 3 and x are separate, so that's why the x is out of the radical, but the 3 is in the radical.
You can see when the light comes on. I'm like, is that enough? No. Can we do another light? Okay, is that enough? There we go, he got it.
How did you find the relationship of sine wave equals cosine of 90 minus x?
You need to review last year's material. I haven't got time for that one. So we have another special right angle triangle. If we take this right angle triangle here, where it's isosceles. We take this right angle triangle here, where these are isosceles, then what are the unknown angles? 45. Have a go at finding what is the sine of 45 degrees without a calculator. Use the technique we just used on the last one. I will pause the video for a few minutes, 5 minutes. Okay, 1 more minute to finish. Okay, everybody, if we can just be quiet, sit down. Sit down. I've got 6, 7 minutes. I'm going to finish this, so I can't take that many questions on this one. Let's have a look. What we just did now is one of the most important things on this course. I give you a problem. It's well within your grasp to solve it. You need to struggle and solve it on your own. Those of you who wait to have me explain it or wait to have somebody else explain it without struggling through are not going to develop problem-solving skills. This is an easy problem to solve. I've just done a very, very similar problem. So it's only a slight shift of what was previously asked of you in order to get you started. I came around for those who were struggling. The only hint some people needed was to be told that this is x. So if we take x as this side, this is an isosceles triangle. We should go to this side being x. Notice this step that I'm taking each time. Instead of putting up equation that comes completely out of space with no idea where it's come from, I tell the reader this is based on Pythagoras' theorem. So I said last time by Pythagoras, or Pythagoras' theorem gives. If you just write up random equations, I need to know it's true. To know it's true, what is it based on? So it's based on Pythagoras' theorem. So this side here is the one we need to find, the hypotenuse. So the hypotenuse squared is going to be equal to x squared plus x squared. This means we've got 2x squared equals h squared. So h is going to be equal to x root 2. So I've got the side here now. This is x root 2. Notice that I'm not bouncing all over the page in random directions. I've chosen where to start, so I've got a bit of space. I'm either going to go straight down here, or I'm going to go over here in columns next to this point. So I think at this particular point, that's my setup. I go over here, and then from the trig definitions, sine of 45 degrees is opposite over hypotenuse. Opposite is x. Hypotenuse is x root 2. So this is 1 over root 2. Cosine of theta of 45 is going to be the same. The tangent of 45 is going to be the opposite over the adjacent. So x over x equals 1. So these different values we've collected so far lead us to the exact value table. You need to be able to generate this table on an exam for yourself. And there's a pattern to it. It's based on those values, there is a pattern. So let's just watch how we generate it with the pattern. We typically just need the angles from 0 to 90 at this point. So here we've got x in degrees. And we just do this on a paper, and then we're going to have the sine of x. We're going to have the cosine of x. We're going to have the tangent of x. The angles that are of interest are 0, 30, 45, 60, 90. There's a pattern to these. It jumps in a couple of ways. We're going up by 45 degrees every other one. We've got a pattern here going up by 30 degrees, and so on. There's a pattern to these. Next up, we put in our values. There's a pattern to these. So what we've seen now is sine starts off here, then we get a half, we get 1 over root 2, we get root 3 over 2, and we get 1. That's all you need to memorize. That's all you need to memorize. In fact, you only really need to memorize these 3. And the best way to memorize is to know roughly what the size of each one is, because it's getting bigger and bigger. A half, as you will learn, is 0.5. 1 over root 2, 0.707. Root 3 over 2, 0.866, something like this. So you can roughly estimate, or well, I use that helps me to know, okay, this is the smallest, this is the medium, this is the larger of those 3, and the rest is the pattern. This pattern here is this one. It's the reverse of that. So this is root 3 over 2. This is 1 over root 2. This is a half, and this is 0. Tangent can also be defined. So we say that the tan of theta is equal to the adjacent over the hypotenuse. You can take the other ones. We've got the sine of theta.
Wait, isn't it opposite over?
Sorry, thank you. Opposite over adjacent. Opposite over adjacent. The tan of theta is opposite over hypotenuse. The cosine of theta is adjacent over hypotenuse. So rearranging these two, we can say that the opposite is h sine theta. Are we good? How can we define the adjacent? So don't say cos, because that doesn't mean anything. You have to say cos of something. Cos theta, cos x, cos 15. You can't say cos. It doesn't mean anything.
Opposite is equal to h sine theta.
So this one is going to be h cos theta. So the opposite is h sine theta, the adjacent is h cos theta. So let's stick them into this formula. We get h sine theta, we get h cos theta. How does that simplify?
Sine over cos.
So this is the definition of how we can define tan. It's a trigonometric identity. Tan theta is sine over cos. So what we have to do is we divide that number by this one. So on the exact value table, 0 divided by 1, still 0. When we divide this by this, notice the denominators are the same. So they don't matter. So this is 1 over root 3. If we divide these, the denominators don't matter. This is 1. If we divide these, it's just the numerators. Root 3 divided by 1. If we do this one, 1 divided by 0, not defined.
There's no tan line.
Okay, that is us finished for today. There's a couple of little IXLs to practice on this one.